Welcome to the final chapter of Chem 1212, Electrochemistry. This video, and the course generally, will not cover either balancing redox reactions by the half-reaction method, nor commercial applications of electrolysis. That said, what is the topic of this chapter, electrochemistry? Electrochemistry is the study of chemical reactions that interconvert chemical and electrical energy. This broadly encompasses two types of systems, galvanic or voltaic cells, and electrolytic cells. A galvanic cell, perhaps more commonly known as a voltaic cell, is a system in which a spontaneous chemical reaction is used to generate an electric current. An electrolytic cell is the opposite, a system in which a non-spontaneous reaction is driven by an applied electric current. As you know, non-spontaneous reactions cannot occur on their own, but that doesn't mean we can't force them to happen by applying energy, like we do in an electrolytic system. Both galvanic and electrolytic cells involve oxidation-reduction reactions, that is, reactions where electrons are transferred from one reactant to another reactant. Since electrical current is the movement of electrons through a conductor, you can probably see how electron transfer can fit into this picture. All oxidation-reduction, or redox reactions, consist of both an oxidation half-reaction and a reduction half-reaction. We can't have one without the other. For our first example of a voltaic cell in action, we'll be considering the reaction represented by the net ionic equation shown here, where zinc metal and copper 2 ions in aqueous solution react in a single replacement redox reaction to form zinc ions in aqueous solution and copper metal. Oxidation, or loss of electrons, is what happens to the zinc. It starts off in the form of neutral atoms in metallic zinc, and the reaction causes it to lose 2 electrons per atom to form the aqueous zinc ions on the product side of the reaction. So we can think of our oxidation half-reaction as producing a zinc ion and 2 electrons from our starting zinc metal. Reduction is the opposite process, the gain of electrons. This is what happens to copper in the reaction at the top of this screen. We start off with our aqueous copper ions, each with a +2 charge. They each have to gain 2 electrons to reach their final state, which is the neutral copper atoms in the metallic copper. So each copper ion reacts with 2 electrons in the reduction half-reaction, forming copper metal. The types of redox reactions you've seen before work like other types of chemical reactions. We put the 2 reactants in contact with each other somehow, and they directly react. For our reaction on the previous slide, we can take a beaker containing a solution of copper ions, which impart a blue color to the solution, and add a piece of zinc metal to get the reaction to start. As expected, we produce zinc ions in solution and solid copper metal. As the copper ions are depleted and replaced by colorless zinc ions, the solution's blue color fades. Likewise, we can see the buildup of copper metal on the zinc strip as its ions are reduced to the metallic solid form of the element. Copper metal, of course, is a reddish color, but it looks black on the bottom of this screen because it's in the form of a finely divided powder. This reaction between zinc metal and copper ions can also happen in a less direct way if we set our reactants up in a voltaic cell shown here. Instead of adding zinc metal to a beaker containing copper ions in solution, we can set up 2 beakers. In this case, the one on the left of this diagram contains a piece of zinc metal immersed in a solution containing dissolved zinc ions, and the beaker on the right of the diagram has a piece of copper metal immersed in a copper ion containing solution. If we connect the 2 pieces of metal via a wire, it will provide a path for electrons to flow from one beaker to the other. However, it takes more than just a one-way path for electron flow to take place. If we move electrons from one beaker to another without any other changes, we would start to build up a huge excess of negative charge in one beaker and a huge excess of positive charge in the other, which would prevent any further movement of electrons in the same direction. To complete the electrical circuit, we also need to connect the beakers via a salt bridge, which is just a tube that contains a dissolved electrolyte that doesn't directly affect the reaction. In this diagram, sodium sulfate is used in the salt bridge, but other soluble ionic compounds can be used as well. Once the connections are in place, electrons will start to flow from the zinc side to the copper side. Because electrons are lost from the zinc side, the neutral zinc atoms in the piece of zinc metal will start to be converted into zinc ions that dissolve into the solution. Likewise, since those electrons are flowing into the copper side, they will combine with the copper ions dissolved in that solution to form copper metal that deposits on the piece of copper already present. Each piece of metal, the zinc strip and the copper strip, are known as electrodes. The electrode that loses electrons, zinc in this case, is known as the anode, while the electrode that gains electrons, copper in the diagram here, is known as the cathode. I think the easiest way to remember which one is which is that the oxidation half reaction happens at the anode, and both oxidation and anode start with vowels. Likewise, the reduction half reaction takes place at the cathode, and both reduction and cathode start with consonants. As electrons flow from one side to another, we need to keep the total amount of electrical charge balanced on each side, and this is where the salt bridge comes in. To balance the negatively charged electrons flowing towards the copper cathode, we need positively charged cations, in this case sodium ions, to flow into the cathode chamber as well. Likewise, to balance the loss of negatively charged electrons from the anode, we need negatively charged anions, sulfate in this case, to flow into the anode chamber. It's fairly easy to remember which ions flow which way, since the cations in the salt bridge flow towards the cathode, and the anions flow towards the anode. If you've heard the terms anode and cathode before, it's probably in the context of batteries. And indeed, while there are many different types of batteries, all of them are voltaic cells that operate on the same basic principles as the cell on the previous slide. The negative terminal of a battery is its anode, which we saw is the electrode where oxidation occurs, where electrons are produced, and the site where anions migrate towards. Likewise, the positive terminal of a battery, or any other voltaic cell, is its cathode, the electrode where reduction occurs, electrons are consumed, and where cations migrate towards. To determine the overall cell reaction in a voltaic cell, we need to add the anode and cathode half reactions together. You may notice that the number of electrons generated by the anode half reaction is equal to the number of electrons consumed in the cathode half reaction, and so the electrons in each equation cancel when they're added together. This is a necessary component of balancing any cell redox reaction, and we'll cover this aspect more later. Suffice it to say, though, that electrons can't be created or destroyed overall in a redox reaction. We can use the notation shown here to represent a voltaic cell reaction. We represent the anode half cell on the left side and the cathode half cell on the right side, separating the two by a double line representing the salt bridge. For each half cell, we use single vertical lines to represent a phase boundary. In the case of our copper-zinc cell, the boundary between each solid metal electrode and the aqueous solution containing the zinc or copper ions. The electrodes are represented on the far side of each cell, with the solution components towards the center, since they're the parts of the cells directly connected via the salt bridge. Since the anode is always on the left and the cathode on the right, electron flow will always be from left to right. One of the most important things we can quantify about any voltaic cell is its cell potential, or cell voltage, sometimes also called the electromotive force of the cell. This is a measure of voltage between the anode and cathode, which is equivalent to the electrical potential that pushes electrons away from the anode and towards the cathode. If you're not familiar with the physics of electricity, it can be summed up in this equation here. Electrical energy, which is measured in joules like any other type of energy, is equal to the amount of electrical charge present in an electrical current multiplied by the voltage. Electrical charge is measured in coulombs, which is equal to the amount of charge delivered by an electric current of 1 amp, or ampere, in 1 second. Since voltage, which we can measure with cell potential, is related to energy, we can incorporate it into the equation shown here. The Gibbs free energy, or delta G, measured in joules or kilojoules, is equal to negative N times F times E, where N is the number of moles of electrons transferred in the balanced chemical reaction, F is the Faraday constant, which relates coulombs to electron charge, and E is the cell potential. The Faraday constant tells us that 1 mole of electrons has an electrical charge equal to 96,500 coulombs. Thinking back to thermodynamic standard conditions defined in the previous chapter, we can also define a version of this equation using delta G standard and the standard cell potential. For example, if we go back to our zinc-copper cell, if we know that its standard cell potential is 1.10 volts, we can find its delta G standard value by plugging in N, F, and the provided value for E standard. N is equal to 2 moles of electrons, the number of electrons that canceled out when we added the reduction and oxidation half reactions together. F is the Faraday constant from the previous slide, 96,500 coulombs per mole, and E standard is, of course, 1.10 volts. Because 1 coulomb times 1 volt is 1 joule, and moles cancel, we end up with joules, Since delta G is usually in kilojoules, we can convert to these units by dividing by 1000. This gives us negative 212 kilojoules for delta G standard. Since this is negative, we know that the reaction is spontaneous under standard conditions.